Hi friends, I am Dr.Y.V.Lakshman. Welcome to Theory of Machines classes. In previous session, we discussed cleans construction, and in this session, we are going to learn a special acceleration. We are going to learn about a special acceleration which is Coriolis component of acceleration. Coriolis component of acceleration. We already understood when magnitude of velocity changes, we may get tangential acceleration. When direction of velocity changes, we get centripetal acceleration. Because of change in magnitude of velocity, we get tangential acceleration. Because of change in direction of velocity, we get centripetal acceleration. And when we do get this Coriolis component of acceleration, listen now. If any point carries both rotary motion and radial motion, both rotary motion and radial motion simultaneously, that point will experience an extra amount of acceleration apart from centripetal and tangential acceleration. That extra acceleration is called Coriolis component of acceleration. I repeat, if a point carries both rotary motion and radial motion simultaneously, first rotary motion then radial motion, or first radial motion then rotary motion, in that case Coriolis component of acceleration will not induce. For getting Coriolis component of acceleration, at same point of time both motions should be there, radial motion and rotary motion. Both motions should present simultaneously at same point of time. Both motions should present. Then only we get this special acceleration which is called Coriolis component of acceleration. First you may write one point, then we are going to do a derivation to find Coriolis component of acceleration. Write definition. Write one point. When a point carries both rotary motion, when a point carries both rotary motion and radial motion simultaneously, that point would experience an additional tangential acceleration, an additional component of tangential acceleration, which is called Coriolis component of acceleration, Coriolis component of acceleration. In what mechanisms it is present? In what mechanisms it is absent? Try to think about various mechanisms. In any mechanism, any link carries both rotary motion and radial motion. If any link carries both rotary motion and radial motion, definitely that link will experience this additional tangential component of acceleration which is called Coriolis component of acceleration. In crank and slotted lever mechanism, this is slider, and this is fixed link, this is crank center, this is lever center, and it is connected to a crank like this, Here P is there, and omega L is the angular velocity of lever, and omega is angular velocity of crank, P is a point on slider, okay? What is motion of P? Slider is lying on lever and lever is rotating. Since lever is rotating, every component which is lying on lever also will rotate. A lever is rotating with an angular velocity of omega L. Whatever is presenting on lever, that also will rotate. So along with lever, the slider also will rotate with angular velocity of omega L. That means P also will rotate. P is carrying rotary motion because of rotation of lever. At the same time, the slider is sliding on this lever. The slider tends to move in radial direction like this. I may call radial velocity of slider as VR, man, right? So here, slider is having rotation by virtue of rotation of lever. At the same time, it is sliding on lever in radially outward direction at this instant, man. Sometimes radially outward direction, sometimes radially inward. Okay? So every point of slider carries two motions here, rotation and radial motion. So if any point carries rotation as well as radial motion, that point will experience an additional component of tangential acceleration, which is called Coriolis component of acceleration. Okay? So, write down one point. Coriolis component of acceleration. Coriolis component of acceleration is present in Coriolis component of acceleration is present in crank and slotted lever mechanism, crank and slotted lever mechanism, and Whitworth mechanism. And Whitworth mechanism and Whitworth mechanism. In these two mechanisms, Coriolis component of acceleration is present. How to find Coriolis component of acceleration, we are going to see in later part of this session. Okay? Coriolis component of acceleration is present in single slider crank mechanism? Definitely no. In single slider crank mechanism, no point of mechanism carries both radial and rotary motion. Okay, radial motion, rotary motion is not present with any point of single slider crank mechanism. Write down next point. Coriolis component of acceleration. Coriolis component of acceleration is absent. Coriolis component of acceleration is absent in single slider crank mechanism. In single slider crank mechanism, not only single slider, double slider also, man. Single slider crank mechanism and double slider crank mechanism. Double slider crank mechanism. So here we are going to derive the formula for Coriolis component of acceleration. So here I am taking a link. This link is pivoted at O, and on this link a slider or collar is there. On this link a slider or collar is there. Currently this link is rotating with an angular velocity of omega and angular acceleration of alpha. At this instant, angular velocity is omega, angular acceleration is alpha. At the same time, the slider is moving in radially outward direction with radial velocity of VR and radial acceleration of F. So the slider is moving away on this link from center of O. It is sliding away in radially outward direction with radial velocity of VR and radial acceleration of F. Okay? And on this slider, I am taking one point. I may refer that point as A. I may refer that point as A. A point is lying on slider. A point is lying on slider. Try to think about point A. What is motion of point A? Since link is rotating, every point of slider also will rotate along with link. So point A carries rotary motion. At the same time, slider is moving away. The slider is sliding now. Slider is not fixed to link. Slider is sliding. That means every point of slider carries radial motion. So point A carries radial motion and rotary motion. So definitely point A will experience Coriolis component of acceleration. How much? We are going to derive it, right? So at this instant, I may assume radial distance of A is R. Radial distance of A is R. Radial distance is R, and in this problem R is not constant. R is not constant because slider is sliding away. R keeps on changing, man. Right? Now, at this instant, what is velocity of A? Since point A is rotating along with length, point A may experience a tangential velocity of r into omega. Radius of point A is r, angular velocity is omega. So tangential velocity of point A is r into omega. If any point is lying on turning length, that point would experience a tangential velocity. That velocity is radial distance into angular velocity. At the same time, point A is experiencing a radial velocity of Vr. Radial velocity of Vr, right? So I may refer radial velocity like this, man. Radial velocity Vr. So two velocities are there with point A. One velocity is tangential velocity r omega, other velocity is radial velocity Vr, right? This is initial position and orientation. In a small interval of time, this length may turn by an angle delta theta. In a small interval of time, this entire length may turn by an angle delta theta, and currently slider is here. Slider is here, and I may refer this point as point A dash, man. Initial A, now A dash. Then radial distance here is r dash. Initial radial distance of A is r. Final radial distance is r dash. And the angular velocity of link is omega dash, because here angular velocity is not constant. It keeps on changing, man, right? So alpha is given, angular acceleration is given, so omega will not be constant. Initial angular velocity is omega, final angular velocity is omega dash. And here our point A dash or A experience two velocities again. So what are those velocities? Tangential velocity. Tangential velocity always perpendicular to turning length. What is tangential velocity here? R dash omega dash. Initial radial distance r, initial angular velocity is omega. That is why initial tangential velocity is r omega. But here r is changing, omega is also changing. Now tangential velocity of point A is r dash omega dash. Then radial velocity is also changing, right? Radial velocity is also changing, because here the slider is moving away with radial velocity of Vr with radial acceleration. It is accelerating. That means velocity will change. Velocity will change. So I may refer this as Vr dash. This is initial orientation and this is final orientation. Now I can write like this, man. R dash is equal to r plus delta r. Final radius is equal to initial radius plus change in radius in this instant, in time delta t. And omega dash, final angular velocity is equal to initial angular velocity plus angular acceleration into time. It is in the form of V is equal to u plus at, initial velocity plus acceleration into time formula, right? Final angular velocity omega dash is equal to omega plus alpha into delta t. Similarly, final radial velocity is equal to initial radial velocity plus radial acceleration into time. Radial acceleration into time. It is also in the form of V is equal to u plus at, initial velocity plus acceleration into time. Okay, right. Now I do like this. At this instant, point A is carrying two velocities. One velocity is tangential velocity, other velocity is radial velocity. So I take components of these velocities. I resolve these two vectors along horizontal, along vertical. So what is horizontal component of r dash omega dash? Definitely horizontal component is r dash omega dash cos delta theta. If this angle is delta theta, this angle also will be delta theta. And what is vertical component of r dash omega dash? Vertical component of r dash omega dash is r dash omega dash sine delta theta. I resolve r dash omega dash into two components, horizontal component, vertical component. Similarly, let us resolve this also. What is vertical, what is horizontal component? So if you draw one line like this, if this is delta theta, this will be 90 minus delta theta, again this will be delta theta, man, right? So if this angle is delta theta, what is horizontal component of VR dash? Horizontal component of VR dash is VR dash sine delta theta, and vertical component will be VR dash cos delta theta. Understand? So every vector I am resolving here into horizontal component and vertical component. Okay? So copy this diagram and copy these values, then we try to derive formula for Coriolis component of acceleration. So try to copy. I hope you have drawn. And one more point here, as delta theta tends to 0, sine delta theta becomes delta theta, cos delta theta becomes 1. So these things also we require. When delta theta tends to 0, sine delta theta becomes delta theta, cos delta theta becomes 1. Okay? So write these values also, right? We require all these things in our derivation. Now, let us try to derive. Write down, man. Total tangential acceleration. Total tangential acceleration. Total tangential acceleration. I refer this as AT bar. AT bar means total tangential acceleration. In this case, an extra tangential acceleration will come. Actually, tangential acceleration is equal to r into alpha. In this case, we are going to get some extra, man, r alpha plus something. That additional quantity is called Coriolis component of acceleration. That is why I am using this term, total tangential acceleration. This is equal to rate of change of tangential velocity. rate of change of tangential velocity is called tangential acceleration. So here you tell me what velocity components are acting perpendicular to link. This is link, this is original link. Perpendicular link means like this, man. In this direction, what velocity vectors are acting here? Two velocity vectors are acting. So r dash omega dash cos delta theta plus vr dash sine delta theta. This is final tangential velocity component, final tangential velocity minus initial tangential velocity. What is initial tangential velocity? R into omega. R into omega is initial tangential velocity. That means minus r omega by delta t. Rate of change of tangential velocity gives you tangential acceleration. So this is final tangential velocity component, that is initial velocity component. So rate of change of tangential velocity gives me total tangential acceleration. So in this expression, in place of r dash, you have to put r plus delta r. In place of omega dash, you have to put omega plus alpha into delta t. Similarly, in place of vr dash, you have to put vr plus f into delta t. Let me write it. So a bar t is equal to r plus delta r into omega plus alpha into delta t cos delta theta plus vr plus f into delta t sin delta theta. So this is final component minus r omega by delta t. Okay. So r dash, r plus delta r, omega dash, omega plus alpha delta t, vr dash, vr plus f into delta t into sin theta, sin delta theta, man. So it is sin delta theta. If you simplify this, you get something like this. Total tangential acceleration is equal to r alpha plus 2 omega vr. In the simplification, you may assume cos delta theta as 1, because when delta theta tends to 0, cos delta theta becomes 1. Here you may put 1 and here you may put delta theta. When theta is very small, sin theta becomes theta. So here you may put 1, here you may put delta theta, and you may neglect product of two small quantities. Wherever you get product of two small quantities, you can neglect that product also. Upon simplification, you may get this equation, man, r alpha plus 2 omega vr. Okay. And what is vr? Radial velocity, man. How do you define radial velocity? Radial velocity vr is equal to rate of change of radial displacement, rate of change of radial distance. Rate of change of radial distance is radial velocity, man. With what rate radius is changing? That's what radial velocity indicates. So radial velocity is like, in this simplification, somewhere you will get delta r by delta t. So delta r by delta is nothing but radial velocity. So this is total tangential acceleration. Originally, tangential acceleration is equal to r alpha, but here we are getting some additional tangential acceleration. That additional tangential acceleration is nothing but Coriolis component of acceleration. I may denote Coriolis component of acceleration with ACR. ACR is equal to 2 omega into VR, right? This is one of the very important formulae in theory of machines, right? I already told, man, there are 8 important formulae in theory of machines. This is one of those 8. So very important formulae in theory of machines. 2 into omega into VR. Coriolis component of acceleration. Just copy them, then we go further. right? You might have copied it. Now see here, man, Coriolis component of acceleration equal to 2 into omega into VR. Omega represents rotation, rotary motion. VR represents radial motion. Okay? For getting Coriolis component of acceleration, both rotary motion should be there, radial motion also should be there. For instance, if rotary motion is 0, omega will be 0, Coriolis component will be 0. If radial motion is not there, VR will be 0. Again, Coriolis component of acceleration will be 0. For getting Coriolis component of acceleration, we require both rotation and radial motion. Right? Right, next point. Direction of Coriolis component of acceleration. Direction of Coriolis component of acceleration. Direction of Coriolis component of acceleration can be found. Direction of Coriolis component of acceleration can be found by rotating radial velocity vector. By rotating radial velocity vector. By rotating radial velocity vector by 90 degrees. By 90 degrees. By 90 degrees in the direction of angular velocity. 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 Let us try to understand it, man. So here a link is there. This link is pivoted at O. And this link is carrying a slider like this. And the slider is moving away with radial velocity of VR, and the link is rotating with angular velocity of omega. Okay? Link is rotating clockwise and slider is moving away from center of rotation. Oh, currently slider is here. Slowly slider is moving like this on link. Now, how to find direction of Coriolis component of acceleration? So take, this is center point of the slider. Then hold your pen in the direction of VR. Currently VR is upward. Slider is moving away, right? So hold your pen in the direction of VR, right? Direction of VR. Then rotate this VR vector by 90 degrees in the direction of angular velocity. So I am putting radial velocity vector like this, man. This is radial velocity vector. You have to rotate this radial velocity vector by 90 degrees in the direction of omega. What is direction of omega? Clockwise. Rotate this pen by 90 degrees like this. You will get direction of Coriolis component of acceleration, or simply I may write ACR, man, right? Already we defined. So this is direction of Coriolis component of acceleration. Okay? Rotate radial velocity vector by 90 degrees in the direction of omega. Your radial velocity vector is upward. Put your pen like this, man. This is radial velocity vector. You have to rotate this radial velocity vector by 90 degrees in the direction of omega. Currently omega is clockwise. Rotate this pen by 90 degrees like this. So this pin give you the direction of Coriolis component of acceleration. Okay? So please copy this. Let us see a few more cases like this. Same case we have taken here, man. In this given problem also same take I took. Slider is moving away with the radial velocity of VR and link is rotating clockwise, and we got Coriolis component of acceleration in the direction of rightward tangent, right? So please copy this. Okay. You may have copied. Let's say second case, man, right? Second case. For instance, omega is anti-clockwise. Link is rotating anti-clockwise. Link is rotating anti-clockwise and slider is moving away in radially outward direction. So what to do? So put your pen in the direction of radial velocity. VR is upward. Put your pen like this. And you have to rotate radial velocity vector by 90 degrees in the direction of angular velocity. What is direction of angular velocity here? Anti-clockwise. So put your VR here, put your pen like this in the direction of VR, then rotate this pen by 90 degrees in the direction of omega. In this case, direction of omega is anti-clockwise. Rotate this pen by 90 degrees in anti-clockwise direction. So this direction gives you direction of Coriolis component of acceleration. So always Coriolis component of acceleration don't act towards right. Sometimes rightward, sometimes leftward. Okay? So please copy this also. I hope you copied. Let us see another case, man, right? Let us see another case. The link is rotating anti-clockwise with an angular velocity of omega, but slider is getting down with radial velocity of VR. The slider is coming towards O. It is getting down, or it is moving in radially inward direction. So this is VR. Now what is the direction of Coriolis component of acceleration? So what you do is, put your pen in the direction of VR. Here VR is downward. You have to put VR like this, man. This is VR. Then you have to rotate this VR vector by 90 degrees in the direction of omega. What is the direction of omega? Anti-clockwise. So rotate this VR in anti-clockwise direction. So definitely this is direction of Coriolis component of acceleration. By rotating VR vector by 90 degrees in the direction of omega, you can find direction of Coriolis component of acceleration like this. So in this case, Coriolis component of acceleration acts towards right. Sometimes it is right, sometimes it is left. Okay? So we finished first part of the derivation, man. So still second part of derivation is there. We have to find another acceleration. We found acceleration perpendicular to link, and we are calling that acceleration as total tangential acceleration. We require to find another acceleration, man, parallel to link, right? Write down now. Total acceleration, total centripetal acceleration. You may write like this. Total centripetal acceleration. Total centripetal acceleration. Total centripetal acceleration. I denote this total centripetal acceleration as AC bar. It is rate of change of velocity parallel to link. Total tangential velocity is rate of change of velocity perpendicular to link. Centripetal acceleration means parallel to link. Tell me, man, here, which velocity component is acting parallel to link? This is the link. Here, what velocity vectors are acting parallel to link? So this is acting parallel to link. This is also acting parallel to link. So there are two velocity vectors which are acting parallel to link. So I can write like this: VR dash cos delta theta minus R dash omega dash cos delta theta. Here I am putting minus y. One vector is upward, other vector is downward. So I am treating upward component is positive, downward component is negative. So this is upward, this is downward, that is when negative. So this is final velocity component parallel to link minus initial velocity component. What is initial velocity component? At this instant, which velocity is acting parallel to link? VR is acting. See here, man. VR is acting like this. So, minus VR by delta t. Rate of change of velocity parallel to link is total centripetal acceleration. Just like previous part of derivation, here also treat cos delta theta as 1, sin delta theta as, here no sin delta theta, no problem, man, right? Treat cos delta theta as 1, and you know what is VR dash? VR dash means VR plus F into delta t. We know what is R dash, R plus delta R. We know omega dash, omega plus alpha into delta t. Let us write it, man. So A bar C is equal to VR plus F into delta t cos delta theta minus R plus delta R into omega plus alpha into delta t into cos delta theta. So this is the final component minus VR by delta t, okay, by delta t. If we simplify this, the total centripetal acceleration is equal to F minus R omega square. You will get this, man. Total centripetal acceleration equal to F minus R omega square. F minus R omega square. You can easily understand this formula, man. Without derivation also directly you can write it. For suppose, if the slider is fixed to link, how much centripetal acceleration will act on the slider? The slider is fixed to link. It is not sliding, man, right? How much centripetal acceleration may act on the slider? R omega square. What is direction? Centripetal acceleration always acts towards center, man. So R omega square always acts like this. This is direction of R omega square, man. And what is direction of F here? F is upward, R omega square is downward. What is net acceleration parallel to link? Simply F minus R omega square, man. So without derivation also, directly you can write the total acceleration formula. Now what is total acceleration of point A? Maybe I may think this point as A. What is total acceleration on point A? Point A is experiencing two accelerations. Tangential acceleration, centripetal acceleration. What is total acceleration? Resultant of these two acceleration is total acceleration of A. So first you may copy this, then we are going to write resultant acceleration or total acceleration of A. So please copy these 2-3 steps. I think you copied. So before writing total acceleration of A little discussion on total centripetal acceleration. It is very easy to understand and it could be handy in doing problems, man, right? Total centripetal acceleration is not always F minus R omega square. Sometimes F plus R omega square also, man. Sometimes F minus R omega square. Sometimes F plus R omega square, depending upon direction of radial acceleration of slider. For example, here a slider is there. This is omega, right? definitely the slider will experience a radially inward centripetal acceleration. Always centripetal acceleration is r omega square, which is always directed towards center of rotation. Omega may be clockwise, omega may be anti-clockwise. Centripetal acceleration is always acting towards center of rotation, man. So either clockwise omega, anti-clockwise omega, centripetal acceleration is always directed towards center. For suppose radial acceleration is upward. Radial acceleration is upward. What is total centripetal acceleration? F is upward, centripetal acceleration is downward, so definitely it is F minus r omega square. R omega square is always acting towards center, but slider is moving away from center. They are acting in opposite directions. That is why F minus r omega square. Okay, please copy. Then we do one more thing. In this case, A bar C is equal to F minus r omega square. F minus r omega square. Because F is acting upward, r omega square always acts towards center of rotation, right? Okay. Now, second case, r omega square always directed towards center of rotation, but in this case, radial acceleration is also F, man. Radial acceleration is also F. So in this case, what is total centripetal acceleration? F is downward, r omega square also downward. The total centripetal acceleration is F plus r omega square. What is direction of this A bar C? Towards center, like that, man, because both accelerations are acting towards center. Please copy this. So total centripetal acceleration is, sometimes it is F plus r omega square, sometimes it is F minus r omega square. F minus r omega square. Now, resultant acceleration of A. All of you write down resultant acceleration of A. So simply I am writing A here. A means total acceleration or resultant acceleration. So this is equal to A bar C square plus A bar T square. So A bar C acts parallel to link, A bar T acts perpendicular to link. These are two mutually perpendicular vectors. How do you find resultant of two mutually perpendicular vectors? Like this only. So A bar C whole square plus A bar T whole square under root. So try to recall parallelogram law of forces, right? Same parallelogram law can be applied for accelerations also, right? So like this you can find total acceleration of point A. If you want to find direction of total acceleration, you can write like this: tan pi is equal to A bar T by A bar C. If you want to find what is direction of total acceleration, you can use this formula: tan pi is equal to A bar T by A bar C. Here pi is angle between total tangential acceleration and resultant acceleration. Angle made by resultant acceleration with link, or angle made by resultant acceleration with A bar C. So even you can find direction also. Okay? So please copy. Right? Now in GATE exam, they may give questions like this. They give a collar rod system like this. This is O. On this rod, a collar or slider is sliding with radial velocity of VR, radial acceleration of F, angular velocity of omega, angular acceleration of alpha. So like this they give, man. Even they provide radial distance also, man, right? They provide radial distance R also. Radial distance R also, man. Okay. So what is total tangential acceleration here? Total tangential acceleration A bar T is equal to R alpha plus 2 omega VR. 2 omega VR. What is direction of R alpha? Tangential, man, right? R alpha acts like this. This is direction of R alpha, tangential to link. What is direction of Coriolis component of acceleration? You can find direction of Coriolis component of acceleration by rotating radial velocity vector by 90 degrees in the direction of omega. Omega is clockwise. I'm rotating like this, man. So R alpha is acting like this. 2 omega VR also acting like this, man. This is R alpha and this is 2 omega VR. Both are acting in same direction. And what about total centripetal acceleration A bar C? In this case, F is outward. And what is direction of centripetal acceleration? Centripetal acceleration R omega square is always directed towards center. So R omega square direction is like this. And F direction is like this, man. So that is why F minus R omega square. You should be careful about direction of these vectors, man. In total tangential acceleration, there are two components. If both are acting in same direction, you have to add. If they are acting in opposite direction, you have to subtract, man. Similarly here, if both centripetal acceleration and radial acceleration acts in same direction, you have to add. If they act in opposite direction like this, you have to subtract. So be careful about direction of these vectors, man. So they may give a collar rod system like this. And they may ask you anything, man. They may ask you what is resultant velocity of A or resultant acceleration of point A. Maybe this is point A, right? What is resultant velocity of point A? Resultant acceleration of point A, or sometimes simply what is Coriolis component of acceleration on A? Or what is total tangential acceleration on A? Or total centripetal acceleration on A? They can ask you anything, man. Anything they can ask. It's very, very famous kind of problem. Many times in GATE exam, this kind of problems came. In coming session, we are going to do some problems on Coriolis component of acceleration. So this is end of the session. And until next session, have a great day. And do join for next session for doing problems with Coriolis component of acceleration and also total acceleration of rotating disk. So both are important. Do join for next session. Until next session, have a great day. Thank you.